Okay, this is our second lecture on stacks. In this video, we're just going to talk about an example of how we might use stacks to convert, or to, I should say, to evaluate postfix expressions. A couple of announcements that will become more specific as time goes on, but Project 5 is out and it is optional. And also make sure that you stay up on the Zybooks readings. So one application of stacks is evaluating a kind of arithmetic expression, notation, known as postfix. Just to start off this, there is something called prefix notation, in which operators or operations come before the operands to which they're applied. This is sometimes called Polish notation. Postfix is just the opposite. It's where the operators come after the operands to which they are applied. So some examples, we're all used to infix, where the operators come in between the operands. Prefix is where the operator comes before the operands. And postfix, finally, the operator comes after the operands. And we can translate between infix and postfix. Postfix has advantages, and so does prefix for some of the same reasons, is that it removes the ambiguity of infix expressions. If I've got an expression A plus B times C, we need precedence rules to disambiguate the order in which those operators might be applied. So multiplication would be performed before addition, for example, using precedence rules. If there is a tie in precedence, we evaluate simply from left to right. And of course, we can use parentheses to specify and overrule any convention or standard precedence rules. So here are some postfix expressions and their equivalent infix expressions. You'll notice here that in the infix expression, multiplication is going to be the first operation that's applied. And in the postfix expression, it is the first operation that appears. And when this operation appears, it's a binary operator, so it has two operands. It's applied to the two previous operands, B and C. The addition is the second operation to be applied in this expression, and it's applied to the prior two operands as well. One of them is going to be, one of those prior operands to the addition is going to be whatever BC multiplication evaluates to. The other is going to be A. And my cursor has left me again, and so I'd be circling these things so you could see them better, but hopefully that gets the picture across and you can take a look at that and think about it. For the second instance of a infix to, here we got the cursor back, the second instance of a postfix expression. In this example, subtraction is going to appear first, and subtraction is going to appear first in the postfix expression. So this would be applied to the previous operands, A and B. This multiplication is the second operation to be applied, and it's applied to its prior two operands, C, and whatever this evaluates to. And you can confirm that for this last example as well. Postfix expressions have real advantages for in a number of computer science applications, notably compilers though. A compiler will translate an infix expression in which there is ambiguity into an unambiguous postfix expression and then typically evaluate that. And when we evaluate a postfix expression, we're going to be using a stack. In this video, we're going to concentrate on that first problem of how to evaluate a postfix expression. In the video that follows this, we'll be using stacks again to convert an infix expression to a postfix expression. So how are we going to use generally a stack to evaluate a postfix expression? We're going to assume that all the operations are binary, and that's important for our examples. We're going to have a stack that stores operands. or values. And these are going to be things like A, B, C. They're going to be integers in our examples. And we're going to scan an expression from left to right. Every time we see an operand, we're going to push it onto the stack. Every time we see an operator, we're going to take the top two elements on the stack and think of those as the top two, the two operands for the operator. And then we're going to pop the stack. And then we're going to evaluate the operator on the two results that we just popped off, and then push the result back on the stack. When the expression has been all scanned, there should be a single number on top of the stack, and that is going to be what is returned by this evaluation procedure. So here's an example, 3, 10, 5 addition multiplication. And I want you to pause the video for as long as you want and picture what is going to happen with this expression. You're going to be pushing operands, and you're going to be popping them off and applying operators when you encounter operators. See if you can visualize this in some natural way and think it through and figure out how to get the result. So go ahead and pause the video and come back when you're ready. So when we see that 3, we're going to push it on top of the stack. The 3 is a operand, push it on top of initially empty stack. Scan the 10 and push that on top of the stack. Find the 5, that is an operand, push that on top of the stack. Now we've got 3 items on top of the stack. And then we encounter this operator. And so what we're going to do when we encounter that operator is we're going to take the top 2 elements off the top of the stack. We're going to apply the operator addition to them, and then we're going to push the result back on top of the stack. When we scan this multiplication, take the top 2 items off the stack, apply the multiplication, and push the result back on the stack. I had said here when we started this video that we started with an initially empty stack. That's actually not a requirement, but when we're all done, there might be stuff below here that was pushed on before. But when we evaluate this, this item that's left on top of the stack, even if it's got some things below it, is going to be the result for that evaluated expression. So here's another example. Do the same thing. Pause the video and visualize in much the same way that we did for the last example what you think the outcome is going to be. So pause the video now, start it when you're ready. So here we start with initially empty stack in this example. We scan the 1, we push it on top of the stack. We scan the 3, also an operand, push it on top of the stack. We scan the operator, and we pop these items, grab the tops values, and then pop them and apply the operator to the result, or to get the result, and we push that result back on the stack. We come to the 2, push it on top of the stack. We come to the multiplication operator. Last, we grab the top 2 items. We apply the multiplication operator, and we push the result back on the stack. And so that 8 would be the result of the entire evaluation process. So take a look at some C++ pseudocode, and this is incomplete pseudocode, but it gets the point across, and it's close enough that you could undoubtedly actually implement it in C++. We're going to be taking what we hope is a legal postfix expression. We're going to be looking at characters one by one in that. You can ignore that. That's a function of the PowerPoint that I used to edit this. We are going to be checking to see if the character we just scanned in is an operand or an operator. If it's an operand, we're going to push the operand on top of the stack. Otherwise, if it's an operator, and we're assuming that's the only other possibility, more robust code might check for other possibilities, but in our case, we're just going to assume it's the only other possibility. We pop the 2 items off the stack, grab their values first, put them in appropriate variables, op1 and op2. The order here is important. particularly for operations like subtraction or division. We compute the, apply the operator to the operands 1 and 2, and then we push the result back on the stack. So here's an example at the top in blue, top right in blue, and we've got an initially empty stack in this case. So that postfix expression at the top, I want you to take a look at it. I want you to pause the video, and I want you to think about what's wrong with it, because there is something wrong with it. It's not major. Won't stop us from using it as an example, but pause the video and think about what is wrong with it and restart when you're ready. So what is wrong with this postfix expression is it has one less operator than it should. If all these operations are binary, and they are, we should have one more operand than we have operators. And in this case, we've got 6 operands and we've got 4 operators. So we're actually missing one. And what will happen when we evaluate this is by the time we process that and we've processed the entire string, we're going to have 2 items on top of the stack rather than just 1. And then we'll deal with that when we come to it. But that's a problem with this, and our code would have to deal with that. So the first thing we do is we scan in left to right. We scan the 5. The 5 is a operand, and we push the 5 on top of the stack. Scan the 7. We push that on top of the stack as well. We scan that addition operator. It is not an operand. So we come down here, we pop the items off the stack after grabbing their top values. 7 becomes the value of operand 2, 5 becomes the value of operand 1. And then we're left at this point with this empty stack. Now we're going to apply the addition operator to the arguments, and we're going to push the result back onto the stack. So 5 plus 7, push that result back onto the stack. Now we're going to jump ahead, and we've got that 12 there that we just placed on, but we're going to go through a number of operands. For each of them, we're going to push them on top of the stack. So by the time we hit this multiplication operator, this is what our stack looks like. We're going to grab the top 2 values, 2 and 3, put them into the appropriate variables, operand 2 and 1. This is what the stack will look like when we're done with that part of the code. We apply the operator, multiplication operator to the operands, and we push the result 6 back onto the stack. We get the 5, we push it on top of the stack. We now have the subtraction operator. We grab the top elements 5 and 6, put them into the appropriate variables in order. And this is what we have for our stack after popping those elements. We apply the subtraction operator to 6 and 5 and push the result of 1 back onto the stack. Now we get to the division operator. Again, we're going to pop the top 2 elements off the stack after grabbing their values and putting them into the appropriate operands. And this is what the stack looks like. Now we're going to apply the division operator to those arguments. 4 divided by 1 is 4, push the result back on the stack. And at this point, we've scanned all the operations, and we've got a problem here because we don't have a single value. Remember, we had too few operators relative to the operands. We're going to go ahead and just complete this example, but your code, if you were to convert this, translate this code to real C++, you'd want to deal with this problem of too few operators and return an appropriate result for that integer value that you're supposed to be returning in the case where you had an error. Here we have or throw an exception or do something else. We're going to complete this with an additional operator that we need. We're going to pop these items off the stack, place them in the appropriate operands. apply the operator, and then push the result back onto the stack, and then return that result, presumably down here. So we finished with our demonstration of the evaluation of postfix expression using stacks, and we will turn next in the next video to how we translate infix to postfix with stacks.